afterwards, you went to Hawaii with the Subaru. And then the next postdoc is now in Swinburne, okay, in Australia, so quite far. And she came here to tell us about what is development so far.
Yep.
Okay?
Yeah, ya está. Yeah, indeed. I'm actually going to be talking about a type of galaxies that has been kind of ignored or basically undetected for a while. And actually, so by type of galaxies, it's something of a rather abstract concept. For example, since I started my PhD, I've always been dealing with like early type galaxies. But what do we mean by early type galaxies? It's actually a mixture of many different types or families of galaxies. Initially, it was kind of established because of this like long-standing picture of the turning fork. It was basically done with a visual morphology classification, where, okay, I'm going to try to press the right one, where you have this early type kind of spiral, ellipticals and lenticulars in the side, and then they thought it would be evolving to more like spiral thing. But then, that was at the very beginning, let's say, when we didn't have that many instruments and developments, but we started to measure many other properties from the galaxies, like sizes, stellar masses, luminosities, their kinematics. And once people started doing that, we realized that this kind of like two families starting to be more diffuse, and I'm a little bit jet lagged, so I might say it a little bit of like weird things, or if I fall asleep, just shout at me. But these type of galaxies would wiggle a little bit in these diagrams, depending like if you would classify them by their rotation or their colors and stuff. Another thing that help us understand what the types of galaxies are is when you put their properties once against another one. That's something that astronomers love to do, scaling relations. You have any of the properties and you put it against another one and you try to figure out what that is telling you. For example, these are some of the most well-known by now, and again, I'm focusing on the early type galaxies, where you have like the size of the galaxy with the luminosity, the stellar mass, and the velocity dispersion. And you can see that there's kind of like a relation, there's kind of a continuity that you could picture out. But actually, if you separate them by these kind of families of galaxies, you see that the picture is even more constrained. You see that all the types, like different colors, are kind of concentrated in specific areas on the diagrams. And they all kind of follow the same color patterns. So since my early starts here in the PhD, let's say, I've been kind of dealing with, that's my diagram. That's my main scaling relation that I've been using. That it's the size with the stellar mass. And basically what it's telling you is that the most massive galaxies tend to be larger than the less massive ones. And there seems to be this continuity that is very steep at the beginning, and then it kind of like flattens out, starting with the ellipticals, and then dwarf spheroidals. And then there's like the globular clusters, and then it's another story. But basically, for many, many years, that was kind of like what the early type family of galaxies kind of was considered. During my PhD and so on, and let's say while I was in the northern hemisphere working, I was focused in this very top end of the massing relation, of the mass relation. So this is a zoom of the area, and what we were doing here with Nacho and Alejandro and many others was actually to try to find these very compact and massive galaxies that represent the relics in the early universe. So I spent a lot of time like up here, let's say in this end. But then I moved to Australia, so I'm upside down. I see things in a different way, and one of the other things I do, besides changing my shift, is I also have been using a different set of telescopes, so it's no longer the ones in here La Palma, or not the ones in the ISO, so now I've been using basically Keck data. This is me, where it says, please don't stay here, and that's basically before the mount like kicks me. That ends my face. And the other thing I've done then is focus a little bit my interest from the massive end to the lower mass ones. There's been all this development where we've been, as I said, so at the beginning it was more of a morphological thing, and then we've been pushing and pushing both the technology, and we now have state-of-the-art instrument in the ground-based telescopes, but we also have all these amazing satellites. And this has provided that we are pushing farther to see way like at the beginning of the universe. But one extra thing that this gave us is that on the meantime, because all the sensitivity is getting so much bigger, we've been able to find things that are way closer than we expected that we could not see before. And that's what I'm talking about, like illuminating the faint universe. So now in the diagram that I showed before, now we have another types of families that were not there. We have this area now that follows the ellipticals is now populated what it's called compact ellipticals down to ultra-compact dwarfs, linking what was before, as I said, those globular clusters that were there with like alone. Now they seem to have a way to go than there. And there's also these other galaxies here, the ultra-diffuse galaxies, that seem to follow more this dwarf path. So in this talk, I'm actually going to be talking about two of these families, first on the compact ellipticals and then on the ultra-diffuse. Why? Because, well, we need to understand why are they in that position in the diagram. Are they intrinsically, let's say, just low-mass galaxies and faint? They have an intrinsic origin. Are they there since the beginning? Or it's more that they moved along these places because they had external influence. Yeah, they suffered harassment, they suffer truncation, starvation, whatever. External processes that made them change, so they were something bigger and larger before. This is, we all know about this issue, the nature versus nurture problem, and it's crucial to understand what are they. So we can study their properties, but we need to see how they fit into this evolution. So as I said, the first part of the talk is going to be in the compact ellipticals. So just a brief introduction about them. Compact ellipticals clearly follow the early type, the elliptical branch. To date, there are about 200 of them that have been studied or even analyzed. They have the stellar mass range between 10 to the 8 and 10 to the 10. But like this is the dwarf, they have smaller sizes, less than 1 kiloparsec, but they have really, really high densities that makes them so different also to the dwarfs. So there's basically two ways to understand these galaxies. As I said, we're talking about the nature or the nurture. So are they intrinsic objects, or have they evolved from something larger? And there's obviously, as always, thing wouldn't be so easy otherwise, observational hints from both sides. So we have in favor of them being stripped objects that, as I said, they have these high densities that are exactly as the ones we see in the center, in the core of the massive galaxies. They, as we saw in the plot before, they follow that elliptical branch like perfectly as a tip and so on. More importantly, I guess, they are usually found close to their companion and mostly in dense environments. But I guess like the smoking gun of this was that not too long ago, we were able to catch some of them in the act, being stripped in that moment by a larger galaxy. So all these things seem to point out that indeed this compact elliptical family is basically just stripped. So they were larger ellipticals or spirals that moved down to the diagram because they lost their entire stellar mass and size. But at the same time, we see some other properties that they don't really match with that. First of all, we found some of them that are in complete isolation. There's nothing around it that could explain that stripping. So that would point out to that these galaxies must have been formed there, as they are now. Although there's also a more bizarre, if you want, explanation that they say that they are runaway remnants. So they were in a dense environment, they were stripped by larger galaxies, and then somehow they were kicked out of that environment, and then now are poor things they're populating alone, but small and compact. But then, when we study the stellar populations, you compare, for example, what we consider might be the progenitor, the host, the one stripping, and the compact ellipticals. The stellar populations don't really match. And then there's been a few cosmological simulations that predict that actually most of these compact galaxies should be formed in situ rather than be stripped. So all this seems to point out that they are rather simply low-mass compact galaxies. So what happens is that, as I said, we have all these properties that are against each other. And even for M32, that is the closer one, and it's kind of like the case study for compact ellipticals, there's so many options, like there's not even a consensus yet, and that's the one we have like right next to the corner. So the problem is that not even for the closest one we can really be secure of what is their origin. But also the problem is that, as it happens when there's a new type of galaxy, the samples are really low. So most of the works either focus on having a slightly large sample, but then only one property, or they might do only one galaxy in more detail. So you cannot really say what's going on with the entire family, let's say. As I said, we have these galaxies that we see them being stripped, so you know that they are stripped objects. But if you put them in the scaling relations, you cannot know if they are done. For example, so these ones here, we don't know if that's just started being stripped. It's still going to be stripped. So their position in the diagram still is not, it's unknown. So you cannot really derive fundamental relations if things are still going to move around. So what we need is to have a large sample covering as many parameters as you can, and then try to see what all these properties tell us. So that's what we've done in this work. So basically what we went is let's see the galaxies that have been already like in the literature. If they have slow data, we want to do the stellar population, so we need a signal to noise at least more than 20. So we have robust measurements. We try to cover as many stages as possible, and I'm going to go into more detail on what this means now, and also the different environments, because as I said, they are mostly found in cluster environment, but there's been also found in groups and even in isolation. So we go to the literature and we start digging which ones do we have. So there's, for example, this is probably the up-to-date, the largest sample. This one has like 150 galaxies. And then some other study cases that they have been published in individuals. And then we also try to find some of these new objects ourselves in the Sloan database. We actually found 6 new ones that they were not reported before. This is so in pink, this is my sample, and then Norris et al. Is one of the other catalogs. So basically, you see here, this is the number with the stellar mass. We are kind of covering the mass event, because it's Sloan data, so the sensitivity is not that good. Kind of the sizes are quite well represented. And this is the different stages that we consider disrupted within halo, near host, and no host. I'm going to talk about it now. And then we can see that the majority of them are found in the group, but they're equally almost cluster and field galaxies. So by this no host and so on, what I mean, and now I'm going to show what I consider a little bit nice pictures, because I usually work at spectroscopy, and I always have like really ugly things. So for once, I think I can show some nice pictures. So these are the galaxies that we consider to have no host. So you see that all of them are here, and at least for a few kiloparsecs, there's nothing around that could be considered a host. Yeah, so we studied the projected distances and the relative the velocities. There's nothing around that could really explain them being stripped. Then there are the ones that are near a host, so you can clearly see which one could have been the galaxy that caused the stripping, but there's no signs of interaction. And we've actually studied deeper images from pan-stars and other catalogs, and we cannot find anything like lower level going on. So we cannot say for sure which they are. But then studying the relative velocities and so on, we could figure out which one of the galaxies was their host. Sorry. Then, like inside this group, but we decided to treat them slightly different, are these three ones that we call them within halo, because they are really close, but they are so much embedded into the halo of the massive galaxies that we cannot really tell if there's something going on or not. But they kind of belong to the with host. Finally, the ones that we have no doubt about it because we see them being stripped. And actually, the good thing is that even for like 2 cases, we have 2 of the galaxies, 2 compact ellipticals, being disrupted or stripped by the same host. Okay, so we have these 25 galaxies. We've kind of separated between these classes. And now what we do is try to derive as many properties as possible. We're not going to just do one and see what we get from it. We're going to get as much as possible. So we have the sizes, we have the kinematics, so then we can derive the dynamical masses. We can do the star populations, getting the ages and metallicities from the line index measurement, but we can also study the star formation history from the full spectral fitting, and we can also get their abundances, both from the indices and from empirical relations. So from this side, we can also get the stellar masses of these objects. So what we do with all this? Obviously, our correlations. We go back to the plots we had before, and we see how their behavior or their place in that plane tells us. So we start by the one I said that it was my one, that it's the size mass. Background is literature galaxies of all types. Here, rather than just, you don't really focus on the symbols, but more on the colors, yeah? So we're gonna go through it. I'm not gonna spend too much detail. If you obviously want to talk about the particular one, we can talk about it later, because otherwise I would never end. But basically, we just kind of see how these colors move in the plot and if they are telling us something. So for example, from this one, what we can see right away is that A, these ones that are considered near the host, that by default we think that they would be the ending product, yeah, of this stripping, they're all populating this like kind of like lower mass and lower size, which this is compatible with them being this lower end. And actually here there's N32 for comparison. On the contrary, all the ones that are currently being stripped are mostly populating the middle part. So they could be still moving around. And actually, these 2 ones here have slightly larger sizes and slightly larger stellar masses. So this could indicate that these 2 have started to be disrupted. But again, with only these, which is one of the properties, we cannot say it for sure. We need more information. So then we go to the mass metallicity one, that is the other one that can tell us a lot about there. Basically, this line here is the one that galaxies in the Sloan follow for the mass metallicity. Again, usually it says that more massive galaxies have higher metallicity. But if they have been stripped, what it means is that at a slower mass, they would keep this higher metallicity, right? So let's see where they are in this plot. There's kind of a partition at 5 times 10 to the 9. Larger than that, we see that all these galaxies kind of follow the mass metallicity regime. So they could be compatible with being intrinsic galaxies. And for the ones that we see them being stripped, this is indicating us that then they are just starting because they are still following the relation. But instead, all the ones that we assume that they are these remnants of the stripping process, that are all the blue ones, they have all these way higher metallicities than expected by their stellar mass. So all this is compatible with them being done, or at most at very late stages of this stripping process. Interestingly, because I said we have these no-host ones that we don't know at all if they are remnants or they are intrinsic. There's this guy here, and unfortunately it's behind. Oh, well. This is a no-host galaxy. And it has very extreme metallicities compared to their stellar mass. So it could be one of these runaway galaxies that have been proposed. Again, we need more information, so from the metallicity, we see what the stellar ages of these galaxies can tell us. And right here, you can see there's like 2 big differences on the colors. We have all these galaxies here, all except for that same one that I was talking about. They're all very young. This is luminosity-weighted ages. This comes from the line indices. So it means that it's biased by the last burst of a star formation, but still, this means that there was something going on recently, which could indicate that the stripping was done on a spiral type kind of galaxy, because there has to be gas remaining, yeah, on the galaxy in order to have more star formation. On the contrary, again, all these done, like stripped galaxies, they are quite old, around 10 gigayears. They have a metallicity that's slightly higher, as we showed in the previous plot, but not incredibly big. So it means that nothing seems to have happened on the last gigayear, I mean, since 10 years ago, kind of. So it would be more compatible with being a kind of like elliptical galaxy that had been stripped. From this plot, then, we also see that the no-host ones are kind of in between. They have like intermediate ages, and and the metallicity, as we see in the plot before, it's compatible. We have two special ones, though, here. We have this one that it's currently being stripped, but it has an intermediate age, like the ages between being so young, but also as the no-host ones, but also the metallicity is quite low. So it could indicate that, because we see it, so we know it's being stripped, but it could be one of these intrinsically already like low massive galaxies that now is being stripped. And then there's this other one that it's way older than anything else, and it's kind of compatible with the metallicity relation, and I'm gonna come back to it in a second, because it's a very interesting one for me. So as I said, there's this hint that they are younger, so it might be a spiral that it's being disrupted, while the older ones might be an elliptical type. So we studied the star formation histories, because we really want to know what happens when the stellar mass is created, yeah? This is what these plots are showing. So this is a typical star formation history plot, where you have the age, where at the beginning is here, so we are now here, with the mass fraction. So it's like how much fraction over time is created. One thing you have to be aware with when you do full spectral fading and star formation histories, don't take each single burst as a face value. You rather need to understand it, like say, fit Gaussians on it. So for example, you can see that for the no host, all of them have these extended star formation histories, all of them. While if you go the ones that are done or being disrupted, you see that they all start quite early in the beginning, and there's kind of two types. There are these ones that have a very peak formation at the beginning, and then they just like fade out. Instead, there are these other ones that show two clear bursts, one very old and then more recently. So this is basically telling us when things happen. So for example, for these ones, this type of star formation history, extended low star formation rates, is compatible what has been shown for low mass early type galaxies. So it would be totally compatible with them being simply low mass compact galaxies. Instead, for this one, we see that the ones that have this second peak of formation are, again, meaning that the stripping occurred very recently, and when it occurred, it formed further star formation history. So it happens if the progenitor, the original galaxy, was a spiral-like, so it had some gas remaining. While in the ones that are more compatible with what we understand for like the exturbation, yeah, they just form and then they just like died out when they are done, we cannot tell when the stripping occurred because it seems to be more an elliptical galaxy. So if you remember, there were those two special cases that I just mentioned about 2 seconds ago. This one is the low, like no-host galaxy, and it shows this very, very, very early formation, and then nothing else happening. And that's what we were finding with the relic massive galaxies. So we can have relic galaxies at lower masses too. It's just that they will have to have this characteristic. So this might be the first candidate for a relic galaxy, but that was originally like really low, low mass and really compact from the beginning. Whereas for the other one that was here, see, the star formation history is exactly as we see for the other no-host one. So once again, it's showing that it's compatible with being a galaxy that was very compact and very low from the beginning, but very recently has been started to be stripped. Okay, so I've been through all these properties and what they tell us. So what you do, you don't need to look at the yeah, words. Just what we do is we have all these properties. So we put them and we see what each one of them are telling us. Yeah. So we need to know what is their origin, in which stage are they? So if they are one of these strip galaxies, are we seeing an early stage? Are they done? Are they in an intermediate phase? And also, if the information that we get can tell us what type of galaxy were they originally. Once you have all this there, so these are the no host, the ones that have a host, and the ones that are being stripped. So you go through all this, and then you kind of decide and see. So the ones that are in green means that all their properties are compatible with the same. And again, I'm going to give you now the final number, so you need to look at all of them. Only the ones that are in this orange is one of these properties might not fully be compatible, but adding all the information that we get from the other properties, we can decide. But there are a couple of them that the results are totally inconclusive. So what we find is that we can secure the origin. We can say which are for sure strip galaxies, which are for sure these intrinsically low mass galaxies. And not only that, but for 75% of them, we can say at which stage they are, and also what type of progenitor they had. And this is important because when we are having, for the satellite, the missing satellite problem and stuff like that, or when we are doing census of of galaxies, we are missing a large fraction of galaxies that they have changed, and they should be considered, for example, elliptical galaxies. But now they are no longer elliptical galaxies; they are these compact ellipticals. So we need to understand better how many of these numbers are there. And 1 second. Most importantly, I guess, is that we find that most of our objects are compatible with this stripping origin, which means, again, we cannot give a general conclusion for family, because we only have 25 objects out of the 200, if you want to know. But the majority of them are compatible with being stripped objects, which means that this mechanism is the one that is shaping this type of galaxies. But still, there are some of them that are intrinsically low and are there, and they need to be taken into account, but they've been ignored or couldn't detect them for a long time. But they are there. So these are just the numbers. For example, we have, as I said, 21 of the galaxies are truly being stripped. And we can tell that 7 of them are at the latest stages, so they are already in place, kind of. But there are 6 of them that their position in the diagram is going to change with time. So we cannot say if they're just going to be compact ellipticals or they're going to be like farther stripped and become, for example, UCDs. What comes now is that, as I say, this is only for compact ellipticals. We need to extend the same type of exercise because it's clearly that we need all the information. We cannot just rely on one of the properties because it gives ambiguous solutions. So we should do this kind of exercise, but for a larger, and also go into lower masses with the ultra compact dwarfs. To do that, I got some recent data with ESI and DEMOS at Keck, and I'm planning to submit a large proposal at ISO. So with that, we can put further constraints and also see what happens with the companions, the UCDs that are at the very low end. One thing that I did not mention, because it doesn't really give us much information, there was another discriminant, there was another property that we studied in this part, and it's the correlation between the dynamical mass and the stellar mass, because it's seen that these galaxies show dynamical masses that are way higher than their stellar mass. So there are many ways that you can explain that. You can have an extremely supermassive black hole, you can work with the IMF, but the stripping origin would also totally explain to why they're up here, because they lost their stellar mass, but the dynamical mass is still okay. So what we want to do, and to date there's only 2 or 3 works that are working on the supermassive black holes on compact ellipticals or UCD, is we want to see if we can detect some of them. So we had a proposal last round for doing this on Symphony for some of these galaxies that I've just introduced, that are the pentagons here. So we submitted it. Now we're waiting for the results. So let's see what happens. And something that is totally out of my hands, so I'll please beg it. We need more simulations. We need more theoretical part. Now, we're only using the stellar tracks from Pfeffer 2013, and it's for UCD, so we cannot really and these theoretical tracks basically explain how these galaxies can move in this diagram. But we totally need to understand better how these galaxies behave if they are being stripped or not. So please, simulators and theoretical people, work on this. And, oh, okay, I'm actually really fast. Okay. Any question in this side, I guess, before I move? Because this is going to be way shorter because it's work in progress, so, yeah. What's up, sorry?
You're saying that the mass vibration of those things is very high.
Mm-hmm.
You're assuming that when they're getting stripped, they're moving to stellar mass, not the dark matter.
Yes, you also lose the dark matter halo. That's the first part.
Maybe the other way around.
Oh, sorry.
We use the mic. In the
Sorry.
I would intuitively think it works the other way around. That dark matter, it's more extended, so you should start losing dark matter and then you lose the stellar matter.
Yes, that's why those theoretical tracks, they kind of like explain you, oops, wait, I can actually go back to here, I guess. Yeah, those theoretical tracks explain, so it's a process. It's not something that just happens. There's first a part that you lose the stellar mass, and then there's a part when you start shrinking and getting like smaller and so on. Dark matter presence is one of the other explanations for this presence. So there are 4 things that can contribute on this happening, but nobody has really worked on that.
What I'm saying is that I think
Yeah,
dark matter would go the other direction, intuitively. I mean, I'm not doing the simulations.
Yeah, no. Dark matter is the first part that is being stripped.
Yes, that's what I'm saying.
With the stellar mass. But the velocity dispersion, if it's driven by the supermassive black hole, you're just going to have all the information. All these things are very concentrated stuff. So, and this is actually, sorry, dynamical mass to stellar mass ratio versus stellar mass. So this means that these have like larger dynamical mass than the stellar mass. But usually they are compatible. It's just like some of them show these extremely large ones. But as I said, this is something that needs to be studied. But at least, as I said, on the UCD ones, they're assuming that first you lose the stellar mass, which also is going to strip part of the halo, the dark matter halo, and then you have a second phase where it shrinks finally and so on. But nobody has really worked on the dark matter halos.
And couldn't it mean that those things are not relaxed? That
yeah.
the dynamical mass that you're measuring might...
They could, but yeah.
Okay.
Do you want the questions now for this part? Or?
Yes, I think so, because like the other part is not that much.
Okay,
if
so
you want.
I have many then.
Not so.
So well, just.
Okay,
just
well, I don't know then. Maybe we should carry on.
Okay, now the first question is that why don't you have used the stellar mass density profile to explore the origin of whether you have either disruption or not, because the stellar mass density profile, particularly if these galaxies are denser at the center, will tell you also what could be the origin or the galaxies that you could link before.
Yeah, because I'm just doing a spectroscopy.
Yeah, but but use that because it would be extremely useful.
Yeah.
Because, for example, when you connect the metallicity with the mass of the galaxies, you are connecting with the mass of the galaxy that you would have after the disruption, but you don't know what is the origin. So when you say this galaxy is weird or not, you would have to have a previous estimation of what was the amount of mass that was removed.
Yeah, we kind of like point out what type of elliptical or spiral must have been, what kind of like, and they are compatible with being 10 to the 5 and 10 to the 11 stellar masses, solar masses, galaxies originally. But yeah, but I think we also need better photometry for the images, because we're doing
what
the one. The problem is that the ones that are being disrupted is really hard to
Which
separate.
is the typical redshift of your galaxies?
What's that?
Which is the typical redshift?
Like a 0.00.
Okay, so they are relatively
I think the
average,
farthest one was 0.004, something like that. But in general, they are all of them quite close. Yeah.
Because I find extremely natural to have dense galaxies at all masses. So I think
well, that's why we have some intrinsic ones, that they are totally
But
compatible
I
with
think that when you, I mean, it would be extremely straightforward to make the comparison of the stellar mass density profile of all those galaxies that you are exploring, and you say that they have different origins.
Yeah.
It would be difficult. I mean, my guess is that they will have a similar stellar mass densities profile, because they are similar masses, similar sizes. So it would be very difficult to say that one is coming from one origin and the other one is from another one.
That's kind of why we also would like to have the black hole estimates, because that would be another straight discriminant on their origin. If their supermassive black hole is larger, then they have to be probably stripped. Well, if it's following like, so 10 to the 5 or something like that, 10 to the 6, that's what you would expect.
I don't think that you can use all
in
this.
In general, yeah, in most of them.
all this for that, because I mean,
the numbers.
imagine that the galaxies, these galaxies are born naturally dense.
Yes.
Then you will expect they have a higher mass black hole.
Yes, but
like
not that much. Even following the ones from the Relic Galaxies.
But you would expect also the metallicity is higher, because I mean it's because metallicity probably is very much linked to the density of the object, and these objects are following the density of the most massive ones.
Yeah.
So I don't know.
Yeah. Oh,
Yeah, I think it's well.
okay. Oh.
I think we should.
Sorry, I'm messing up.
I think
Okay,
we
I'll
should
carry on, and then we'll just come back to it.
ask questions.
Yeah.
Just
Sorry,
to
yeah,
be
yeah.
kind of
Okay.
following the natural path.
Let's go to the other part of the talk. As I said, this is pretty much work in progress. We're submitting hopefully very soon, but there's this other type of galaxies that it's on the other side, let's say, of the branch. Yeah. So as I said, these ones go down like very steep and following the entire properties. Well, there are these kind of like flattening out properties, and UDGs are here in between. So UDGs are a type of galaxies that have 10 to the 7, 10 to the 8, roughly stellar masses. They have extended sizes compared to, for example, the compact ellipticals we were talking about, that are more compatible with like ellipticals. And there are many other properties. There are some people here in the audience that have worked a lot on this, so they know a lot. So they have, for example, dark matter profiles that are larger or quantities than dwarfs. They're found in all types of environments. Initially were pinpointed in cluster environments, but now we're getting more cases of them in field and groups. So the thing is, there's all these kind of properties that make them very intriguing, because there's kind of like two scenarios that can explain them. Either they can be kind of failed giants. This is like galaxies that primordially you had this stellar halo that then it failed to create the bulge and so on and evolve. And this could be maybe because they have infall in the cluster environment that has not allowed them. There's also the other part that they are a type of dwarfs. If you've seen that in the plot, they kind of follow the dwarfs path. And in that sense, they could be also kind of failed dwarfs in the sense that they could also be dwarfs that were created in the outside environment and then fell into the cluster and they lost it. But there are other, as I said, this is a very recent field and there are so many different types of explanation to form these ones. There are also ones that they say that just simply because they are, they live in the high spins, so they are basically just the low end of the dwarfs. They say there's other ones that say that they can be shaped just by internal processes, so you don't need them, because the problem with this scenario here, is that you need the cluster environment then, so you could not be able to find them in the field, as we do. Well, these other works here say, well, if you have this like outflow-driven gas feedback that just removes it, then you can just have them in the field too. As I said, many of them is like, because we see them in the cluster environment, it has to do that they were like larger galaxies, larger dwarf galaxies that infall in the cluster, so they were like reshaped. They get these more spheroidal shapes now. And for example, here Roman and Nacho were showing that this could be the case. For example, the ones outside have these bluer and younger properties than those in the cluster that are redder and let's say older. So it could be that these galaxies are created outside the field, but then are reprocessed as they fall into the cluster. So once again, there are all these different scenarios. And one thing that has been a little bit elusive to date is the star populations analysis, similar to the one I just showed before. Because these objects are really, really faint and are extended spectroscopically, are very hard to have a good signal-to-noise spectra. It's very demanding. You need a lot of hours in the large telescope, and even so, you will see that it's not that amazing. There's been some attempts from the photometry point of view, but still, you need the spectroscopic ages, but also star formation histories to see what's going on with them. So what we did was we had time at Keck. We created a mask for coma, and then we observed this field for about 14 hours with Keck. We had another field, another mask that was external. We only had 2 hours. So for that external mass and this internal mass, we have only recession velocities. But for the central mask, we could obtain the star populations for some of them. As I said, even though if you put a lot of time, the spectra are not that amazing as one would expect. You are dealing with a lot of issues from the sky and contamination. So from the, I think in this mask there were about 20 UDGs. We only got 7 of them that have enough signal and at least do a star population analysis. We also included a few other dwarfs and spirals in the mask, so we could do the same analysis and see what they look more like. This is actually the spectrum. You can see some of the most prominent lines. You have H betas, magnesium B, and then some of the irons that we use for the stellar populations. And the fit is what we retrieve if we use the full spectral fitting. Okay, so when you do the star populations and you derive the ages, the metallicities, the abundances, the star formation histories, exactly in the same way that I showed for the other ones. So I'm not going to go into detail now. We're going to see how they compare with the predictions. So, for example, if we look at the stellar ages of these objects, so this is the prediction from Wrong et al. 2017, that it's based on simulations that if these galaxies are a type of late-forming dwarfs, right? And they have this spread of age, which is also compatible with some other simulations, but that they peak around 7 or 8 gigayears. And we see that all our objects, basically all of them except for 2 of them that are slightly younger, are totally compatible with it. We are adding here 5 other galaxies that have spectroscopic analysis to date. And I'm going to show them right now. So this is promising. What we are getting seems to be compatible with the predictions, but again, sorry. Yes. What's up? Dwarfs, yeah, late dwarfs. Yes, yeah. But it's also compatible, I think, with Chang 2017, that it's another type of simulations. It's very recent. Late-forming dwarfs. Yeah, they assume that they were formed because of the later infall in the cluster. Yeah. Mm-hmm. So, like the properties of the UDGs, because they are created later in the. Yeah. So again, we go back to these scaling relations, and we look where they are, how they compare with everything else we know. Okay, there's a lot of points, so I'm just going to go through all of them. Stellar mass, our main indicator, with the H, the metallicity, and the alpha abundance. Our UDGs are the blue dots, and then we have the spirals from our sample, from our observations, in yellow, and the dwarfs in our sample in these gray round circles. Then I'm adding here a bunch of early type galaxies of all stellar masses from COMA, from my study in 2014. I'm adding here all these red dwarfs from Smith et al. 2009. And again, the background ones are like literature literature data of all types. This is the scaling relation for the H mass from Thomas et al. This is the one from Galaxy for the for the mass metallicity, and this is the one from Kirby et al. 13 for low mass systems. And this is the one from Thomas et al. For the alpha. The problem is that, like usually for the massive N, we only get to usually 10 to the 9. Some of the works 10 to the 8, but we are usually not well behaved on the lower part. The other symbols in black, as I said, are these other spectroscopically confirmed galaxies. So these 3 are from Gu et al., so they're also coma galaxies. And then these 2 are from Pania, 2017. One is from coma, the other one is a field galaxy, a field UDG, that is DJSat. So what it's pretty straightforward to see is that in all the cases, our galaxies cover the same and follow the same properties as the coma dwarfs of Smith et al., right? And it actually follows very nicely the predictions from the more massive ones. Like, in particular here for the metallicity one, we see that the metallicity relation for low mass galaxies is actually kind of low compared to what we see. That's something that Smith et al., they already kind of like pointed out when they were studying their dwarfs in coma. They rather seem to follow this more massive edge. We find, as I said, well, this spread in ages, that it's compatible, but still, usually they are not very old, and I think that's the important part of it. They have intermediate ages, they peak at the 7 gigayears, but they're not 14 gigayears old, let's say. That's important, because it kind of exclude the failed giant one, because they are supposed to be very old, just from at the beginning, yeah? In the metallicities, here I'm talking about total metallicity, not iron over hydrogen. So these are slightly in the range of minus 0.3, minus 1, as I said, higher than the scaling relation, but more compatible with has been seen before for other dwarf galaxies in coma. And the most interesting one, and that's something we are working on in more detail in another case, we have these alphas, we have these abundances, where we see they are actually kind of more enhanced than one would expect for lower mass systems. In particular, we have one of the galaxies that has a really, really high alpha, which that's kind of unexpected at this regime. But again, they actually would follow very, very nice, most of them. One last thing we can look at is at their star formation histories in the same way that we did before. We want to see when the mass was created, yeah? So this first plot here shows the average star formation history from the coma early types that I showed before. And it kind of showed that things in coma kind of were created early on, and then they had like more extended times because we see different infallings and so on. But the bulk of the galaxies, the more massive galaxies in coma, are formed like very early on. On the contrary, all our galaxies show this delayed star formation epoch in the sense that they all started at least around 10 gigayears ago. 3 of them, actually, they show these very SSP-like star formation histories with very low metallicities, and 2 of them, they show a recent burst that is more solar enhanced, compatible of like the later infall in the galaxy and interacting with the surroundings. So, and that's only like 1 or 2 gigayears ago. But they're all compatible with, this is the stellar mass that we're talking, the stellar mass weighted properties. So all the stars in this were created later on, not, let's say, primordially. So, and this is, let's say, the most recent part of it. This is 10 hours in DJSat. This is a field galaxy, so we're no longer in the cluster environment with the KCWI new instrument at Keck. Study, we wanted to do Muse type, let's say, radial properties, but again, it's really, really hard to work with UDGs. That's something we are very impressed on. This work is going to be shown by Nacho, but I don't think he's going to be talking about this next week. But you can talk to him in more detail, and I'm not going to spoil his results. But this is, for example, this is a 10 hours KCWI spectra of this UDG in the field. Again, we have these very prominent lines on the H beta. We can see the magnesiums and some of the irons, so we can do the star populations and full spectral fitting. And one other property that he's finding, and that goes with the sense what I just showed before, this galaxy is extremely enhanced on the alphas. And what it means, actually, when you look at the other at the abundances, is it's not that it has an overabundance of magnesium. It seems actually that it has a really lower abundance in irons. So we are now studying on what's happening exactly with these galaxies that seem to have a weird behavior on the iron side, not on the magnesium. So, as I said, this is kind of the results that we have found in this last paper. And we find these intermediate ages, quite low metallicities, but slightly overabundance alpha patterns, and kind of stellar, single burst of formation for most of the UDG. So all this is more compatible with this scenario where the galaxies have this later infall, so they're created later on, than these primordial halos that then they just like failed to do anything. So yeah, they're more compatible with the late forming dwarfs, but there are some properties that they are not, still don't understand, like these huge alphas that we need to figure out. So as I said, this is work in progress, so we are hopefully getting some more data soon and finding out more about it. So yeah, stay tuned, and thank you.
So now is the proper time for questions. So
Sorry,
let's
my
start
bad.
here.
Okay, Anna, for the first part, when you were speaking about the compact ellipticals, a compact elliptical, if you look at the density, it's like a stone with a halo of gas.
Yeah.
So if you put that stone in a harsh environment, you strip it, and you're
left with
the core. Why don't you extend that for the what you call relic galaxies? Because the relic galaxies are massive galaxies. You say that the majority of these mid-sized galaxies are formed by stripped.
Mm-hmm.
Why don't you extend that idea for the relics, which are more massive?
What do you mean? We have.
So you agree that the relics are a result of a stripping as well?
Not as one. So the relics that we study, because we use the exact same things, we are for sure, it's like those low mass intrinsic galaxies. There might be some of the compact, so the thing is, some of the compact massive galaxies are not all the compact massive galaxies are relics, and you were in the paper too.
No.
So those, why they are compact and massive, but they could have been stripped. But the ones that we call them relic galaxies,
Exactly.
we know they are intrinsically compact and massive galaxies and nothing happened, because we've studied all the properties in the same way as these ones. So we know that those ones, they cannot be stripped. But
So
that doesn't mean that there are not other ones, but you cannot call them relics.
So all the relics are
All the relics have
out
to be
of the stripping.
intrinsically...
They were not stripped.
No.
According to you.
No. But there are other compact massive
But
galaxies.
it's funny then, there is not a continuity. You see, you go to lower masses and you see that majority of them are stripped. You go higher masses and you say none of them are stripped.
Well, that's telling you that then
Don't you think
the
that
mass
is
is
like-
doing something.
Yeah, of course.
Yeah, the mass is clearly one of the key parameters to derive one or the two.
Okay, Karma.
But yeah.
Hi. Well, I'm impressed how many information you can get from these little tiny dots. Okay.
Yeah.
Okay. As you know, my field of expertise is star formation histories, okay? And I am a little worried about your star formation histories.
Yeah.
We have been, as you probably know, we have been doing tests comparing results for galaxies which have star formation histories from color magnitude diagrams, really reliable ones, and then from spectra. And we have found actually very encouraging results, something that I would have never expected. In fact, I was very skeptical about this kind of star formation histories, but I have to say that I am impressed. But in one case, in the first paper we published, in fact, the first author is Tomás Ruiz-Lara, which is probably here. We analyzed the field in the bar of the LMC, and we used Starlight, STECMAP as well, and also ULIS, and we found a very good agreement with the STECMAP, but very funny and strange results with Starlight. And you say you are using Starlight. What we found were really very bursty star formation histories for something that clearly doesn't have a bursty star formation history. Also, the bursts that we found were not where they are, because within this galaxy we do know that there is epochs of enhanced star formation, but the burst that Starlight was giving had nothing to do with the epochs of enhanced star formation in this galaxy, and the metallicities were totally off. So my suggestion would be that you...
Can I say,
Yeah.
are you talking about the UDGs or the other ones? Because all,
No.
all the UDGs ones are actually done with the STECMAP.
Okay,
Yeah.
nice. I'm happy
But
to
the
hear
star
that.
formation history I'm showing is with the Starlight. I've done both. I always kind of use both
Okay.
codes, and I
Okay,
compare.
so this was
Yeah.
my question. This is what I was going to.
Okay.
Have you tried with different programs, and
Yeah.
what is the agreement you get? And then the second part of the question was, because the disagreement was even more important with the metallicities, and if the metallicities that you are quoting in the diagrams, were they obtained with Starlight, or were they obtained with a different kind of fitting of the spectra?
Yeah. So actually, completely in that sense, because so I've been in this field of like the full spectral fitting and line indices, and one thing I know for sure is I never just believe one method, which sometimes is a headache because then you start getting discrepancies. But particularly, at least for the average values, I always compare them, and they are completely, particularly for the metallicities, they are on the dot. Actually are the stellar ages that in this case varies a little bit from something a little bit older to a slightly intermediate. But I've checked all of them. And with STECMAP, with the ultra-diffuse ones, yeah. Yes. Well, originally I also did it with the compact ellipticals too. So usually I do line indices, I do full spectral fitting, and I usually use Starlight and STECMAP and kind of compare. The thing with this one in the UDGs, we use as many because the spectra is not superb. So if you do line indices, in some of them, there's some stuff in, I don't know, each beta. So for that one, we cannot do anything. So then I use the star formation histories. So for the UDGs, I made a mixture. I got all of them, and then I compared what do I get, and which is the one I trust the most to put those values. And we found out that for the stellar ages and metallicities, STECMAP seemed to be the most robust. Also, I masked different maskings and like putting different parameters and so on. So in that sense, STECMAP is really good. But then, for example, on the way of, it shows you the star formation history, STECMAP, it's a way of giving you the parameters. Yeah, it kind of like, how to say it? It dilutes to make it a continuous star formation, kind of. You're not gonna have this burst with the STECMAP. It's always gonna, because it just spreads it out between the SSPs that you give it. So it's always gonna give you more of a cumulative stuff. So in that sense, yeah, I'm more used to Starlight because it's the one that I've been using so far. But the ages and metallicities are very compatible with all the methods, with line indices, and particularly the metallicities. That's what something I was really impressed, because usually full spectral fitting are known to be more like failing a little bit more in the metallicity part, and in this case, they were really, really compatible. So, yeah, okay, sorry.
I guess
We can talk about more later, but yeah. Yeah.
firstly a comment, which was you missed the DeCintio paper on.
What's up?
When you put the scenarios, you've missed the DeCintio paper. You put in Amoresco for both scenarios, and
No, it was
this was
there, no?
clearly anyway. Just a comment there.
I was not well positioned. It was.
Yeah.
Yeah, she says it's like
keep going
more.
back.
No. Wait. Hola. Here.
Yeah, here. Okay, so the second internal processes came from...
actually, she was,
the
no, it was there.
Dicentio-
It was there.
Okay, yeah,
Sorry.
anyway, yeah, that's fine.
I can promise you that it was there.
Yeah, you just copied the same citation. Anyway, so...
Oh, yeah, sorry.
With your star formation histories, so you've got these bursts, how much can we trust? I mean, every galaxy that we look at has a very old stellar population in it, right?
Yeah.
All the dwarfs we see locally that you can look at really closely. So you've got these galaxies that some of them just, you're saying, similar to SSP, but at 8 gig years or something. I mean, this would be, how much can we believe that? Because, I mean, this would be a world first, right? It's not very much.
No, it's
yeah.
just that they are, like, they
I mean, we
don't
never see
start
that before in any other
forming
galaxy.
until like 10 giga-years ago, and that's the same star formation histories that they were shown for the dwarfs in coma, this red population of dwarfs in coma from
Okay.
Smith.
But I mean, all of the
Old-
local
it's
dwarfs.
old, it starts, let's say, with a delay. Like around
But
10
every
giga-years ago.
galaxy that we see that we can really get a good star formation history locally has also a very old population, right? So ultra-diffuse dwarfs, we don't see anything that doesn't form galaxies until, you know, for 4 giga-years or something like that. So I'm just asking how much we can trust
The other thing,
this scenario, because it would be very interesting if it was
some of
vaguely
these
true.
galaxies are they show a cusp, so we might be actually biased by what we are. The signal that we're getting might be just biased with this cuspy part of it.
Well, I can tell you that for the LMC, with a spectra with a very high signal to noise and with the starlight, we found star formation histories that were bursty, that didn't have an old population, that were very much like the ones you show, and we know for sure that the bar of the LMC doesn't have a star formation history. This is definite. So these star formation histories, I mean, maybe the average ages, things like this you can trust.
Yeah.
But the star formation histories, you really have to take them with a lot of caution.
Yeah. I
Okay,
agree
a
on that.
lot of
I
caution.
agree on that.
So don't,
Yeah.
maybe. This I would need to, I cannot say anything
Yeah,
about
yeah.
this, but
But
I
at the
can
same
tell
time,
you,
you only get it in this. This is the first time that that we've seen this later star formation objects. So yeah.
no, but
But
I mean,
with the
even the burst at the intermediate ages. I mean, the star formation histories, you have to be very
I
careful
know.
about that.
I agree on that. It's not the
I think this is a
Okay.
very, very
Yeah, yeah.
interesting topic, very
Well, I'm
hot as
gonna be
well,
here
and
the
a lot of
entire
people.
week, so-
how long are you going to be around?
till next Wednesday.
So
Yeah,
there is
that's
plenty of
plenty
time for these technical details discussion. So
Sure.
fine. Sorry.
No, I wanted to say that it was a beautiful exercise we did some years ago when Senarro was here.
Yeah.
He prepared some synthesized star formation histories, and then with different programs we tried to reproduce them. And it was in a closed envelope, let's say. So then we opened the envelope and we saw what we got and compared with the results. And the results were mixed. I mean, there were no program that you say, this is the very, very best. They were competing to each other. So that is a very beautiful exercise that we can repeat. Of course. Reality is...
I think that this is something to take into account. No, I mean, you know.
Yeah, no.
Because I mean, if you try to reproduce from a StackMap, a Starlight, or whatever, something that is coming directly from models, is not realistic.
Once again,
no?
that's why you need to combine all the information and not just
And
rely
we need to
in
talk a
one.
lot.
No, I was expecting that.
Any other question in something that had nothing to do with the star formation history?
So, in fact, I wanted to ask you about the alphas in the first part of your talk. What happened?
In
yeah,
the comma, I mean in the compacts.
Yeah.
They are more enhanced, which is so one other scenario for the UDGs actually is that because they are kind of cuspy, that they can become UCDs because the alphas that we see are kind of similar. So
Okay.
they're not over. Did I put a plot though? I don't even remember. Did I show anything on the alphas here? No.
No.
Yeah. No, I was going to say. They are slightly enhanced, but it's not an over enhancement or anything.
Okay, for the objects in the now for the last part of your talk, the alpha that you determine comes from base models or properly? Okay, then they are more enhanced than what you
I know,
think.
yeah. And there's line indices, so, and
Okay.
we might have some, but that's why the error bars are so big. But I don't know where it is. Nope.
Okay.
But
I think we have to stop here. I mean, we had plenty of time for discussion. So let's thank Anna again.